Okay, so this is the third type of reaction that we're going to talk about in solution stoichiometry. The first two were double replacement reactions. The one resulted in a precipitate, and you can now use stoichiometry, limiting reactions, and the knowledge of concentration to figure out the amount of a precipitate that was made. The second thing we talked about were acid-base reactions, and you've done a titration. You can do the baby math for the titrations. That's done. This third type is a single replacement reaction. The mole lab that you just turned in was also a single replacement reaction. Single replacement reactions frequently not only change up the partners in ionic compounds, but they also change up the number of electrons. The hallmark of a redox reaction is the reactants switch the number of electrons around. This is really vitally important, as the backside of your paper says. We use a redox reaction to power a battery. The first batteries were dependent on that exchange of electrons in order to move the electrons through a wire, yeah? Okay, so for right this moment in time, we will talk about this in much more depth at the end of the year, but for right this moment in time, in solutions, this is what we need to talk about. A redox reaction is one in which electrons are transferred. They must, write this down on your paper, must happen in tandem. You can't have a reduction without an oxidation. There's a mnemonic to help you keep this straight. The mnemonic is Leo, the lion says grr. The cat reference. There is another one called oil rig, but we're going to go with Leo, the lion says grr. This is to help you remember that if a species, if a atom loses electrons, it is oxidized. If it gains electrons, it's reduced. Loses electrons, it's oxidized. Gains electrons, it's reduced. All right, I remember it this way. The oxidation number increases from the reactant side across the arrow to the product side. So when I'm examining that atom, I look for it as a reactant and I see what happened to it as a product. If the oxidation number went up, I know it's the oxidation. The gain of electrons is reduction. The oxidation number decreases across the arrow. One way we need to figure out how many electrons have moved around is to assign an oxidation number to every atom in a chemical equation. We do that by using a bookkeeping method that gives us a visualization of what happens. Right? These aren't real things. This is a bookkeeping method that we've designed. So we're going to assign an oxidation number and an oxidation state to every atom, and we're going to do it according to these rules. So here are the rules right now. So if you find an atom in its elemental form, you assign it an oxidation number of 0. Any atom, as it is in the periodic table, has an oxidation number of 0. So if you saw copper by itself, copper solid, that's the way it's on the periodic table. It has an oxidation number of 0. All the diatomic molecules, so chlorine, has an oxidation number of 0. We write the oxidation number up to the right of the atom, and we include a charge if necessary. All right. The second rule that we're going to talk about is monatomic ions have an oxidation number equal to its charge. What? A monatomic ion in an ionic compound is equal to its charge. Look, let's try this and see if we can marry a couple of concepts in one fell swoop. I know that's unbalanced. This is part of the trick that we're going to learn today, is to balance it. The first thing we're going to do is assign some oxidation numbers to this chemical reaction, to each one of these species. A species means nothing more than a thing in the reaction. This is plain potassium, it's a solid. What is its oxidation number? 0. This is chlorine gas, its oxidation number is 0. This is an ionic compound, each of them are monoatomic ions. Potassium would be +1, and the chlorine would be -1. Now we look at this and say, is this a redox equation? Yeah, because oxidation numbers changed across the arrow. To look at this, we say that potassium went from 0 oxidation number to +1. Is it oxidized or reduced? Oxidized. It lost an electron, yeah? And we would say it lost an electron by adding the number of electrons it lost to the product side. We're going to leave the chlorine balancing part alone, but the chlorine has been reduced because its oxidation number went down. It gained that 1 electron. We clear? Okay. Back to assigning numbers. Nonmetals have negative oxidation numbers. That's true, but boy, you need to write yourself a note. Beware of polyatomic ions. Polyatomic ions are 2 covalently bonded nonmetals that have a charge. We will find that the nonmetals in a polyatomic ion can have a positive charge. Oxygen is -2 in all compounds with the exception of peroxides in which it is -1. In this class, the only peroxide we're going to work with is hydrogen peroxide, which is H2O2. That's the only case where oxygen is -1 and hydrogen is +1. All other times, oxygen is going to be -2. Hydrogen is usually +1 with nonmetals, as it is in water and hydrogen peroxide. It is usually -1 with the metal. Sometimes they form hydrides. It would be -1 in a hydride. Please take advantage of this. The sum of the oxidation numbers in a neutral compound is 0. The sum of the oxidation numbers in a neutral compound is 0. The first thing you have to do in any of these problems is assign oxidation numbers to every atom in the problem. So you have to be fairly good at this in order to move on. I'm going to show, most of the time you can just look at the compound and determine the oxidation number. That brings us to our first problem right now. If you look at the periodic table, those nonmetals in group 14, 15, and to some extent 16 don't play well. They have variable oxidation numbers, and you have to figure it out by what it's bonded to. Let's look at CO2 right now. By inspection, I can figure out the oxidation numbers of both atoms in this compound. Oxygen is not in a peroxide here, so it is -2. This is a neutral compound, and I know the charges will add up to 0. Each one of the oxygens are putting forth a -2 charge. So in order to balance that out, the carbon has to be +4. We write just the oxidation number above, not the charge. Just the oxidation number, not the charge. Sometimes these get kind of trickalicious, and there's something called the algebra method. that will allow you to solve for the oxidation number in almost any compound. So we'll take a difficult one, do the algebra method, and then move on. I'd like to know the oxidation number of each atom in sodium thiosulfate. Thiosulfate is a polyatomic ion. Sodium is a metal, so this is an ionically bonded compound, yeah? To solve for the oxidation numbers in this compound, I first list the atoms in the compound. There's a sodium, a sulfur, and an oxygen. Then I count them. There are 2 sodiums, 2 sulfurs, and 3 oxygens. I know that the charge of all of these atoms will add up to be 0, since it's a neutral compound. Now I'm going to insert in the parentheses the oxidation numbers of the atoms that I know to help me find the atom that I don't know. Which atom do I know? Oxygen is -2. Sodium is +1. And the sulfur I'm unsure about, so I'm going to call it X. So the sodium is putting forth a 2 plus charge. Sulfur is 2x. Oxygen is -6, and that whole mass is going to add up to 0. So I make it a 7th grade algebra problem where +2 plus 2x minus 6 is equal to 0. 2x minus 4 is equal to 0. 2x is equal to 4. X is equal to 2. Then I write the oxidation numbers above each one of the atoms. Oops. And I'm done. Now, the only difference, okay, let's do this one by inspection. The halogens don't have very variable oxidation numbers. The halogens are -1. There are 6 of them, so there's a -6 charge from the halogen. In order to be a neutral compound, the sulfur must be +6. That was an easy one. The nitrate polyatomic ion has an overall charge of -1. So if you were going to do your algebra method here, you'd have to remember that it would add up to -1. So the nitrogen would be +5, and the oxygen would be -2. Now, the standard for AP Chemistry this year is you be able to recognize if a redox reaction is taking place. In order to do that, you assign oxidation numbers to every atom, and you determine whether or not they've changed. This is lithium solid. It has an oxidation number of 0. This is diatomic oxygen, also 0. Lithium in a compound is -1. Oxygen in a compound is -2. Is this a redox reaction? Yeah, it is. What is oxidized? Lithium. And what is reduced? Oxygen. Okay. Now I'm going to refer us to the half sheet, and we're going to be working off of the worksheet, and I'm going to show you how to balance equations. All right. And I'm only going to show you how to balance in an acidic solution because that's what we did in the lab. This is how you are going to balance the equation that you did yesterday. All right. here are the directions. And you know what? I don't know who came up with this method, but before this was nothing but trial and error, and it was very frustrating. Whoever designed this, if you follow these directions exactly as they're written, in one step, you will balance for charge, which is the what you're supposed to do in a redox reaction, and for mass, the way you normally balance an equation. So here's how you have to do this. Divide the equation into half reactions, one for oxidation, one for reduction. Balance each half reaction this way. First, balance the elements that are not hydrogen and oxygen. Then you balance the oxygen atoms by adding water as needed. I don't get that. Oh, look. Let's say you have this going to this. First thing you'd have to do is balance the chromium. Second thing you'd have to do is balance the oxygen. You see that there are 7 here and 4 here. The only way to balance the oxygens is to add water. That's your only source of oxygen. So to this side, you would have to add water. If you added water, you would then unbalance this side because you would have no hydrogens here and you'd have hydrogens from the water here. The only way you can balance hydrogens is to add a hydrogen ion to this side. We'll see this later when we balance the lab reaction. Okay. Then you balance, figure out the number of electrons that are changing. Now, if on each side of the arrow you don't have the same number of electrons, you need to balance the entire half reaction with an integer, the lowest common factor. Then you add everything together. Ready to do this on your own? Absolutely not. Would you like to see a couple of them and build up to the finale? Okay. Let's start with number 14 on your worksheet. Number 14 says that a gold ion and a solid cadmium react, and then the products are the solid gold and the cadmium ion. This is a net ionic equation. There is an anion here and an anion here. They're the same anion, so they were left off, they were spectators. This is an unbalanced net ionic equation. This is very similar to the mole relationship lab where you had silver and copper, yeah? Okay. So now your first step is to find the oxidation numbers for everything in here. These are ions. Their oxidation numbers are equal to their charge. That part's done for you. These are solids from the periodic table. They both have oxidation numbers of 0. Now, you have to identify what was oxidation and what was reduction. I started the oxidation part and I don't know why. What is oxidized here? What has lost electrons? Cadmium. Cadmium, with its oxidation number of 0. I'm going to box this 0 to remind myself in the final equation, we would not put that there. The only charge in the final equation is for ions. That's a reminder not to put it in the final equation. Cadmium solid into cadmium ion. Looking at my directions, do I need to balance this? No. One cadmium here, one cadmium there. If I needed to balance, my only option would be to balance using the coefficients, correct? We know that from Chem 1. Do I have to mess with any hydrogens or oxygens? No. So now I have to make the charge the same on both sides of the arrow, and my tool to do that is to add electrons. This is 0 and this is +2. In order to get them the same, I'm going to add 2 electrons to this side because 2 positive and 2 negatives will balance out to a 0. Now charge is the same on both sides. This is a completed half reaction for oxidation. I'm putting in parentheses to remind myself that it's done. Now, oxidation cannot happen without reduction, and that's good because we see that reduction has occurred. The gold ion became solid gold on this side. I'm putting the oxidation number up there because I'm new at this. It helps me remember, but I'm putting a square around it to remind myself it does not belong in the final equation. There are same number on both sides, don't have to worry about that. No H's, no O's, don't have to worry about that. I do need to balance the charge on both sides. I can only do it by adding electrons, and so I'm adding 3 electrons to this side, so 0 is equal to 0. And I am closing this in parentheses because it's done. Now I am to step C, and I see that I do not have the same number of electrons on both sides of the arrow. So I need the lowest common factor between 2 and 3 to get the same number of electrons on both sides. That would be 6. So I'm going to multiply this by 3 and this by 2. And since I'm new at this, I'm going to rewrite this equation. And then this would be I'm going to add these 2 half reactions together. I see that I have the same number of electrons on each side, and I have to. If I don't have the same number of electrons on each side, I did something wrong. These will cancel. And now I'm ready to write my final balanced equation. I'm leaving these off. My final equation looks like this. That was balanced for mass and for charge in that one step that I followed. Let's do number 11, and then I'm turning you loose. Number 11 has elemental sodium plus elemental chlorine forming the ionic compound sodium chloride. Need to add some oxidation numbers, 0, 0, plus 1, minus 1. Starting with oxidation first, what's oxidized? Sodium went from 0 to plus 1. And 1 electron will balance that half reaction. In reduction, I had chlorine gas goes to the chlorine ion. This is the first time that I have some balancing of mass to do. There are 2 chlorines here, there's 1 here. I balance it simply by doing this. Don't have to worry about the H's and the O's, just moving on. Now, the difference here is how many electrons are moving around. I could picture this in my mind as 2 elemental chlorines that are bonded together. On the other side of the arrow, I have 2 chlorine ions. Each one of these requires 1 electron to balance the charge, yes? So there's a total of how many electrons that move around? 2. Two and 1 are not equal. So I'm going to multiply the entire equation by 2, and I'm going to distribute that 2. And then I'm going to add my 2 half reactions together. All right, what we're going to do for the rest of the period is finish this worksheet and then lead up to balancing the equation from yesterday's titration lab.